Every time you log into an account, you aren't actually sending your password to be stored in a file. Instead, systems use a mathematical proxy, a representation of your data that is far easier to verify than it is to uncover. This process uses a hash function. It takes a piece of data, like the password hello123, and runs it through a one-way mathematical algorithm. The result is a unique, fixed-length alphanumeric string known as a hash. The system's security relies on consistency. Because a specific input will always produce the exact same hash, the system only needs to compare the string you just typed against the one it has on file to grant access. To prevent attackers from identifying identical passwords across different accounts, systems add a salt, a random string of data appended to the password before it is hashed. This ensures that even if two people use the same word, their stored fingerprints remain unique. Since these functions are mathematically irreversible, an attacker cannot simply calculate the password from the hash. This shifts their objective. They don't try to solve the math, they try to recreate the result. Initial attempts usually exploit the most common point of failure, human habit. Using dictionary attacks and credential stuffing, software tests millions of words from leaked databases against a target hash, hoping for a match based on recycled or predictable information. If simple matches fail, rule-based attacks apply automated transformations by appending numbers, swapping letters for symbols, or changing capitalization to account for the common ways people attempt to make simple words feel secure. When human predictability isn't enough, attackers turn to hardware. Engines like Hashcat are designed to offload the mathematical workload to the parallel processing cores of a modern graphics card. This shift in hardware allows an attacker to execute brute force attacks, testing billions of unique character combinations every second until the hardware successfully reproduces the target hash. While Hashcat focuses on raw throughput, tools like John the Ripper emphasize versatility. It can automatically detect different hash types and is often used to analyze offline system files extracted from local machine memory. These methods work best when the attacker already has the data. For live authentication systems, like a website login or an SSH server, they use Hydra, a tool that performs automated, high-speed login attempts over the network. Attack vectors expand from simple human error to industrial-scale computational power, leaving systems that rely on basic character sequences highly vulnerable to discovery. In a typical breach, once a system is compromised, the attacker executes a hash dump. This extracts the stored NTLON hashes, the mathematical fingerprints of every user on that machine, allowing the cracking process to move entirely offline. The attacker loads these hashes into John the Ripper, along with a word list containing millions of entries. The software begins the process of hashing every word in its list and comparing it to the stolen data. When the software finds a match, the plain text password is recovered. The mathematical protection is bypassed because it guessed the input that created the fingerprint. Cryptographic strength remains theoretical when the implementation relies on weak user choices. A hash is only as secure as the entropy of the data that created it. To build a system capable of resisting these attacks, developers must first understand the specific mechanics used to dismantle them. Effective defense is built on the friction created by these offensive tools. Length is the most effective deterrent against brute force attempts. Every additional character increases the possible combinations exponentially, moving the time required to recover the password from seconds to centuries. To eliminate the patterns targeted by dictionary attacks, password managers generate and store long strings of non-human randomness. This ensures that a user's credentials never appear in a leaked word list. Modern hashing algorithms like bcrypt are designed to be expensive. They intentionally slow down the processing speed of each hash, effectively neutralizing the speed advantage of an attacker's graphics card. For live systems, account lockouts and multi-factor authentication provide the final barrier. Even if a password is recovered, the attacker is blocked by a physical device or a timed lockout, ending the automated attack. True security isn't found in a single secret word. It is achieved by layering character length, algorithmic friction, and secondary verification to create a system that is mathematically resilient.